Hello, everyone. This presentation will be about a library that makes it easier to write efficient programs for non-volatile memory. This is joint work with my collaborators, Nama bin David from VMware, Mikkel Friedman and Erez Petrank from the Technion, and my advisor, Guy Balak from Carnegie Mellon University. So non-volatile random access memory is a new memory technology that achieves speeds comparable to DRAM, while at the same time providing persistence, which means that data is not lost after a crash or a power failure. Like DRAM, it is also byte addressable. However, it's able to reach much higher memory densities. In the last few years, this memory has become commercially available, and you can, for example, order Intel's Optane DC persistent memory. So one of the big benefits is that we can now get persistence without having to use SSDs or hard drives. However, the drawback is that persistent algorithms for NVRAM have proven to be very challenging to write. The issue is that caches are still expected to remain volatile, which can cause the persistent memory to be in an inconsistent state after a crash. This can happen for several reasons. For example, suppose a process P makes a sequence of writes W1 to W5 to cache. Because of automatic cache line evictions, an arbitrary subset of these writes can appear on non-volatile memory. And this means that after a crash, we lose our arbitrary subset of writes, which could put the data structure in an inconsistent state. Because of this kind of problem, processors have introduced new flush and fence instructions. The flush instruction takes a memory location and it forces it to be written out to main memory. For efficiency reasons, it does so asynchronously, meaning you can do other instructions while this is happening. The fence instruction synchronizes all previous flushes by waiting for them to complete. So one way we can fix the problem described earlier is by putting a flush and a fence after every store operation. This ensures that the values reach non-volatile memory in the same order that they reach cache, so non-volatile memory is always consistent. However, flushes and fences are very expensive, so we want to avoid using them as much as possible. Also, more challenges show up when we move to a multi-processor environment. So the fundamental problem is that even if you flush after every store instruction, there's still a delay between these two steps, and another process can be scheduled in between. So for example, suppose process P1 writes W1 to cache, and then let's suppose P pauses before flushing the write to non-volatile memory. Now another process Q might see W1 and decide to perform a write W2. W2 can get flushed to non-volatile memory before W1, and if a crash occurs right now, then we are once again in an inconsistent state because W2 depended on a write that disappeared. So what this example shows is that just flushing after stores is not enough, and you might have to flush after loads as well if there's a dependency on the value that you read. And this can start to get very expensive because loads are usually more common than stores. So ideally, we would like to achieve persistence with as few flushes and fences as possible. And this requires answering two orthogonal questions. The first one is identifying which operations need to be persisted. And there has been a lot of work on this topic, both on general techniques and on more special purpose ones. So one solution proposed by Izraelevich et al. Is to persist every load and store instruction. While this is easy to apply, it is not the most efficient. And on the other side of the spectrum, there has been a lot of work on designing specific persistent data structures, for example, by David et al. And these are usually much more efficient, but they are very subtle and hard to design. So regardless of which approach you pick for the first question, we still have to address the second question, which is who should persist these instructions. So in general, you can solve this problem by having every persistent instruction execute a flush. But this could lead to a lot of redundant flushes. So to see an example, suppose P writes W and then flushes it to non-volatile memory. Next process Q performs a persisted read. Which sees W. And since Q has no way of telling whether or not W has already been persisted, Q has to do another flush, which is wasted work. So the question is, how do we avoid these redundant flushes? And ideally, we want to make sure that each persisted write only gets flushed once. And this problem is the focus of our paper. So one way to solve this problem is to track whether or not a memory location has been flushed since the last update. David et al. Proposed a technique called link and persist, which basically uses a special bit on each word to indicate whether or not the value has already been flushed. So in this example, the bit is set to 1, indicating W still needs to be persisted. And after we flush it, we set the bit to 0. This technique is very widely used and has been independently proposed by several other papers. So the advantage is that it's very simple and efficient. However, the disadvantage is that it's not fully general because you can't always find a spare bit in each memory word. And it only works for compare and swap, meaning that you can't do fetch and add or exchange or other atomic primitives on these memory locations. So our paper presents a more general algorithm for tracking if a memory location still needs to be flushed. It works for any atomic read, modify, write instruction, and it doesn't need to steal any bits from the word. Instead, we keep the tracking information on a separate location, which introduces some complications because it can no longer be updated atomically with the memory word. We show experimentally that our more general algorithm is often just as fast as link and persist, and sometimes even faster. We also define a high-level interface for persistent memory programming, and we package all of this into an easy-to-use C++ library. So traditionally, when people implement persistent data structures, they usually program directly with flush and fetch instructions. In this paper, we define a higher-level interface, which is more intuitive to use, and also allows for more optimizations under the hood to avoid redundant flushes. Basically, the interface lets you specify for each shared memory operation. Basically, the interface lets you specify each shared memory operation as either persistent or volatile. Persistent stores guarantee that the written value is flushed before returning, and persistent loads guarantee that the observed value is flushed before returning. Note that it doesn't specify who should do the flushing, and this allows us to apply optimizations under the hood. So finally, volatile loads and stores are used for values that can be safely lost after a crash. And we define this interface more formally in our paper, but this intuitive definition is sufficient for the talk. So this is how we implement persistent stores and persistent loads. We call the algorithm flush if tag, or FliT for short. So basically, the idea is to associate a FliT counter with each memory location. And to do a persistent store, you first increment the counter right to X, then you flush and fetch X to make sure that it is persisted, and finally, you decrement the counter. This ensures that the FliT counter is always larger than 0 whenever the current value has not yet been flushed. So to do a persistent load, you can skip the flush instruction if the FliT counter is 0, and otherwise you have to flush and fetch. In our paper, we show that you don't actually need to fence in the load, but for simplicity, we'll leave it here. So the idea is that the counter should only be non-zero for a brief moment of time during the store operation. So most persistent loads will not have to flush or fence, which saves a lot of time. So you can also view this algorithm as a form of helping, where loads help ongoing stores persist the value that they wrote. So note that persistent stores can be concurrent with each other. And this means that the FliT counter will represent the number of concurrent stores on the memory location. And for most workloads, this number won't be larger than 256. So a single byte is enough to store the counter. Also note that the FliT counter never needs to be flushed to persistent memory because it can be lost after a crash. So we only talk about persistent storage on this slide, but the same algorithm would work for any read, modify, write operation, like compare and swap, fetch and add, etc. And this is one of the benefits of this approach over link and persist. And also the algorithm that we show here is for RACI instructions. Non-RACI ones can be implemented more efficiently because they don't have to access the FliT counter. The performance of the FliT algorithm is affected by where we place the counter. And this affects both space usage and also the number of cache misses. The easiest option would be to put the counter right next to the memory word. However, this doubles the size of each memory word. We could instead have one FliT counter per cache line or one per node, but these are harder to implement as a generic library. What seems to work the best is storing the FliT counters in a hash table. And we can make the hash table much smaller than the number of memory locations, which saves a lot of space. Each memory location gets hashed to one of these counters in the table, and this could cause some collisions. Collisions don't affect the correctness of our algorithm. However, it could affect performance in two ways. First, if multiple memory locations share the same counter, then there will be more contention on it when we do fetch and add. And second, the counter is more likely to be non-zero, which means that load operations are more likely to have to flush. So when we pick the hash table size, there's a trade-off between saving space and reducing collisions. And note that each process can only be accessing one counter at a time. So when we measure collisions, what we really care about is how often do two processes access the same counter concurrently. In our experiments, we see that using a hash table, using a 1 megabyte size hash table seems to work well in practice. This is small enough to comfortably fit in cache and also large enough that collisions are rare. We package these ideas into a C++ library, which does not require any compiler support. To use the library, you basically wrap your data types with this persist type, and then for each load, store, or compare and swap, you pass in a p flag indicating whether or not the operation should be persisted. Our library takes care of adding the necessary flushes and fences to make sure that this happens. If you don't pass in any p flag, then it defaults to being true. So here's an example of how to use a library to implement a durably linearizable lock-free binary search tree. So starting from one that is not durable, you just have to wrap a few data types with persist, and no other changes are needed. So this is very easy to use, and the consequence is that it replaces all the loads and stores in the code with persisted loads and stores. Usually marking everything as persisted adds a lot of overhead, but since our library skips redundant flushes, this actually performs surprisingly well, and we will see some experimental numbers in future slides. A nice thing about C++ is that all RACI variables have to be declared as stud atomic types. So our library can easily tell which ones are RACI and which ones are not. For RACI variables like left and right, we use the FliT counter, but for the non-RACI ones, we use a more optimized implementation that doesn't require FliT counters. Note that if you want to write more optimized code, you can set the default behavior of our library to be volatile and then manually specify which operations should be persisted. So for example, in this code, the load on line 11 is persistent and all the other ones are not. For the experimental evaluation, we applied our library to several lock-free data structures, including a linked list, a binary search tree, a hash table, and a skip list. We also tried 3 different approaches for deciding which instructions to persist. The first method, called automatic, persist all instructions. The second one, called manual, reduces the number of persistent instructions, but it is harder to apply. The third one, NV-traverse, finds a middle ground between these two, where it is less efficient than manual, but it is easier to apply. So finally, for the last question, which is what our paper focuses on, we tried using link and persist, and also 2 variations of our algorithm. The first one is called FliT adjacent, which puts the FliT counter next to each memory word. And the second one uses a hash table of 1 million FliT counters. We also compare with the default solution, which is to put a flush after every persistent instruction. So each of these 3 categories are orthogonal to each other, and we tried all combinations of the 3 in our experiments. Our experiments were run on a machine with 48 hyperthreads and 3 terabytes of Intel Optane non-volatile memory. For the flush and fence instructions, we use CLWB and sfence respectively. And the graphs that I'll show are run with 44 threads, where 5% of the operations are updates and 95% are lookups. So the results for a binary search tree are shown on the left, and the results for a linked list are shown on the right. The dotted line at the top represents the throughput of the non-persistent version of each data structure, which does not perform any flushes or fences. Note that Lincoln persist does not show up in the binary search tree graph, and this is because Natarajan Mittal's binary search tree makes use of the 2 lower bits of each pointer, so they are not available to be used by Lincoln persist. Comparing the blue bar with other bars, we see that avoiding redundant flushes is very important and leads to at least a 2x performance improvement across all the experiments. We also show that both variations of FliT are competitive with Lincoln persist despite being more general. As we move from automatic to manual, we see that the throughput generally increases because the number of persist instructions decreases, and this is as expected. Now let's look at the leftmost orange bar. So this is exactly the example we showed earlier, where we applied FliT to the lock-free binary search tree, to make all instructions persistent. So recall that we just had to change a few types, and it's interesting to see that this simple change actually performs surprisingly well and gets within 50% of the non-persistent binary search tree. So in conclusion, we introduce a higher level programming interface where the user specifies which instructions need to be persisted. We also present a general and efficient implementation of this interface. And the idea is to avoid redundant flushes using FliT counters. And finally, we wrap all of this into an easy to use C++ library. So that's it for this presentation, and thank you for listening.